Yeah, so welcome student to today's lecture. So this MA425 Topology, um, and this is lecture number 8. Okay. So now so far we have discussed about closed set, closed set, derived set, and other things, right? Now we would like to discuss the notion of convergence of a sequence, whatever we have learned in analysis, right? So what do you mean by sequence here? So in a general topological space, so let X be a topological space, a map from as a natural number to X is called a sequence in X. Okay, the same definition what we learn in analysis. Okay, so then obviously when you have a sequence, you want to know whether the sequence converges to a point or not. So you say that, so you write down that. So a sequence so let me write down this by the symbols xn. N belongs to natural number. Okay. So this is a map. So for each one, so this kind of image of that, right? So a map that sends n to xn. Okay, the sequence xn is converges to a point, say x belongs to x. So sequence, so when I'm saying sequence, I mean sequence inside x. Okay, converges to a point x, which is element of x. If something happen, if what? So if for every neighborhood to you, if for every neighborhood, say u of x, when I'm saying neighborhood, I mean open set of x, capital X containing small x. Okay, u of x, you have a there exists okay, so there exists a natural number n naught belongs to natural number such that it's kind of similar definition what you learn in analysis, but little bit general. There exists a natural number n naught such that what happens is that your xn, the element of the sequence xn belongs to this open neighborhood of x u for all n greater than equal to n naught. Okay, whenever your n is bigger than n naught, you all those in all those the tail of the sequence actually belongs to that open neighborhood, and this is kind of a general definition, and this definition also implies the definition you learn in real analysis, right? So in fact, in real number R, when you learn analysis, you are learning under something called that equality and topology, and there the open sets are actually open neighborhoods there, right? So the definition exactly kind of act. Okay, so the question is that whatever you learn in real analysis, that you can ask the same question here also. So does the limit, I mean, I should not say the here. Okay, so does limit of a sequence say let me write down this xn is unique. A simple question one can ask, okay, and you know that the answer for real numbers is yes, okay, but unfortunately this is not true in a general topological space. So the answer no for a general topological space, okay. So it will obviously be yes for some topological space, not for all, okay. So so let me just give an example, maybe. So let me give an example, then you will understand why it is not true. So suppose my x is something, say say 2 points, I have 1 and 2, and I have a topology on x by empty set x and say 1 and 1 2. Yeah, so maybe yeah, this is enough now, okay. Now yeah, so this is my topological space, this is a topology on x, okay. Now here look at this sequence. Say for example you choose a sequence xn, okay. Okay, so now you choose the sequence xn, which is a constant sequence, say 2, taking the value 2 2 2 2 2 2 2. Now natural question, what is this limit? How, I mean, this limit exists or not, and what is the limit, okay. And surprisingly the limit exists, and not only that, the limit is not unique. Now you see that your xn is both convergence to 1 and 2. The limit of xn is 2 and 1, both, like xn converges to 2, and also you must say and xn converges to 1 also, okay. And you will be surprised why, because constant sequence should be, the limit should be 2, right? Why 1? Now you see that by definition of convergence of a sequence to a point x, what you need that whenever you have a neighborhood which contains x, you will have a natural number such that xn, the tail of that is belongs to that open neighborhood, right? For every neighborhood is true. Now you see, look at here, under this topology, what are the neighborhoods of 1? There are 2 neighborhoods, right? Only one. 1 minute, yeah. No, yes, I think I need to change the point. So let me change these points. This topology is 2. So instead of 1, let me write down 2. Yeah, then I am done actually. 2, yes. No, 1 minute. So I have one the sequence. No, I don't need to change actually. I think the 1 is enough, okay. Because if you choose any neighborhood of 1, and then this neighborhood, okay, so let me think little bit what is happening. So yeah, so any neighborhood of 1 that contains this sequence 2. I think, yeah, I need to change it. So 1 is not going to. If I have to 1, then I have to change the sequence 1. So other than that, let me just change the topology by 2, and then it will be working. So any neighborhood of 2 also contains 1. See, I mean, obviously, if you choose 1 here, okay. So I mean, xn converges to 2. This is obvious, because for every such n, it is the same, right? The question is that why xn also converges to 1. So if you choose any neighborhood of 1, so neighborhood of 1 are what? There is only one neighborhood of 1, which is x itself, right? Now obviously these neighborhoods contains 2 also, see. So the neighborhood of 1, which is x, and this also contains 2, so intersection 2, it is actually non-empty, right? And so your natural number n naught is actually the first one itself. When n not equal to 1, then this intersection is non-empty, and hence 1 is also limit point, limit of this sequence. Okay, yeah. So instead of 1, if I see here I choose 2, if I choose 1, then you can send the sequence by 1, then also this is fine. Okay, this is an example I just gave you to show that in general topological space that limit may not be unique. Okay, yeah, so this is one drawback of general topological space. So this kind of space are not so much interesting. Okay, and then one more property I would like to discuss. Now recall in my last lectures, so I asked you some question, because there is some kind of meaning of that question. So let me recall again. So I said that you choose a real number, and then you choose your set of natural numbers. Okay, for example this the natural numbers. Okay, and I ask what is a closure, what is a derived set of A, and I hope you can prove that this is actually phi, and A closure equal to A is nothing but natural number. Okay, so why derived set is phi? Because for every, there is no points of n is actually limit point of n, and obviously no points of R is limit point of n, other than no point of R actually. It can be n also. Why? Because whenever you choose a point, so see when I am saying R, I am assuming usual topology, right? So whenever you choose an element natural number, if it is natural number doesn't matter. So if you choose any element x belongs to R, and it can be natural number n, it may not be natural number n, right? If it is natural number n, then you choose intervals if n this x belongs to n, then what happens? Then this is an integer, right? So then you choose x minus 1 to x plus 1 open interval. You see that these intervals intersections in minus x is actually phi. So that means x cannot be limit point of that set. Okay. Similarly, if x does not belongs to that natural number, then what you do, you choose the distance from smallest integer. So so this is my symbol, maybe x. So what does that mean? That means, so this is the distance from the smallest natural number, means, so for example, if x equal to say 2.35, then distance is 0.35. Okay, if x equal to 2.75, distance is 0.25. Okay, so this is the you can say that okay, so this is kind of, you can say, minimum. Okay, so let me write down properly, then you will understand. This is minimum. So obviously there are two possibilities. It can be before point mid-5, after point mid-5, right? So before point mid-5, and then what do you choose? You choose x minus that integral part of x. Okay, or this can minimum when x is less than 0.5, like 3.5, 4.5, less than that. If it is more than that 0.5, then you choose what? You choose or rather I should say yes, this is fine. Otherwise, what you choose? You choose the integral part of x plus 1 minus x. Okay, so this is kind of minimum of these two things. Okay, which is the distance. So for example, okay, so pictorially 1, say 2, and it is say sitting here something 1.75 your x, then this is the minimum distance. Okay, and then if you choose any open intervals which is less than this distance, then this interval does not intersect, right? So these intervals you choose something, say u, and this u, that this u intersection natural number equal to empty. So the other than natural number also, any other real numbers cannot be limit points, right? So what does that mean? That means the natural number, the closure it itself. So what does that mean? That means the set of natural number inside R with respect to usual topology is a closed set. So this is the conclusion I want to say. This is a closed set. Okay. And not only that, you see that inside R, if you choose any finite set, any finite point sets, that must be a closed set. Okay, the same proof will work. You find out a point of R and you check what is the minimum distance and find out open neighborhood less than that radius, and that will work. Okay, so the question is that is this true that in every topological space this finite point, for example a singleton set, is a closed set always? Okay, so this is again another question I'm asking. Is a singleton set, say for example X is closed in any topological space? Any topological space, is it always closed? For example, I have given an example here that even natural numbers is closed, and if you choose any finite sets of natural numbers, right? So you can say that any finite set of real number R is closed, right? With respect to obviously usual topology. When I am saying R, so I am assuming that usual topology. Okay, so can it be same for a general topological space? And unfortunately the answer is again no. And I can give you the same example. So what was the example I gave last time? So 1, 2, and you choose a topology, for example 5x and singleton, maybe 1 or 2, doesn't matter here. And now you see that this singleton says this one is not a closed set, is not a closed set with respect to this topology. Why? Because the one complement, what is one complement? This is singleton set 2, and this does not belong to the topology, so the complement is not open, and hence the set is not closed, right? So this is one example. Now see, these kind of examples are actually these are kind of discrete kind of sets. Okay, so these kind of examples are important, but they are not so interesting. And if you want to make a space interesting, then it should have this property that limit of a sequence are unique, and this kind of finite point sets or singleton or whatever they are. See, if the singleton is closed, then finite points are also closed, right? This is mathematical induction. So they may not be, should be closed, right? So because of this property, so we need to avoid this property to define such a nice space. And this was due to a German mathematician, Felix Hausdorff. Okay, so what Felix Hausdorff defined nowadays is called a Hausdorff space. I will tell you Hausdorff. Okay, so what is a Hausdorff space that I am telling? See, obviously I will just touch this thing because I need some properties here. Otherwise, these are a part of something called separable axioms that you will learn later. Okay, in details. But let me just give you some of the properties and ideas here. So what is a Hausdorff space? So so a topological space, topological space X. So I'm not writing tau always because I'm assuming that the topology is there. Okay, is say to be a Hausdorff space or T2 space. Okay, some people call it T2 space, Hausdorff space, or some people call T2 space. Okay, if for any two distinct points, any two distinct points, for example, okay, so maybe say x1 x2, so distinct means they are not equal. Okay, there exist open neighborhoods, there exist open neighborhoods u1 and u2 of or rather I should say disjoint neighborhood. Okay, there exists let me just write down, there exists disjoint neighborhood u1 and u2 of x1 and x2 respectively. Okay, what does that mean? That means that is there exists u1 u2 belongs to the topology of x such that x belongs to u1, sorry, x1 belongs to u1, x2 belongs to u2, and u1 intersection u2 is 5, disjoint. Okay, then it's called a Hausdorff space or T2 space. In fact, there are something called T0 space, T1 space, T half space. There are so many spaces are there, and T2 and half space, T3 space, right? For example, T0 space are called Kolmogorov space, T1 space are called Speicher space, T2 space are called Hausdorff space. Similarly, you have something called regular space, normal space, Eurostone space. There are so many spaces are there, and these are you are going to learn this thing maybe after midterm as a part of separable axiom. Okay, separation axioms. So here just T2 is the minimum criteria which is required to make the topology interesting, which is kind of preserve the most of the known properties whatever you learn in real numbers. That's why I'm just describing here. Okay. Now I will show you that this Hausdorff space is very interesting actually, and it actually has the properties of many properties of real number that true here. For example, if you choose a open sets, if you choose a finite sets of points, it must be closed. If you choose some sequence, it must have a unique limit. Okay, so those kind of things true here. Okay, so example for this Hausdorff space, obviously R with usual topology. So I mean that equivalent topology. Okay, usual topology means equivalent topology. Okay. Now I am giving you work. Can you check what kind of space is, for example, the cofinite topology? If we have a cofinite topology in R, can you say anything about that, whether it is Hausdorff or not? Okay, just homework, do it. Okay, and obviously I will prove that these properties that okay. For example, let me just write down a theorem that every finite set means the number of elements are finite. Okay, set in a T2 space is closed. Okay, so what does that mean? That means that the closure of this set is always same. Okay, so what I need to prove? So proof. So suppose let you have A, B, A finite set set in a topological space X, topological space X. Okay, so this is given that A is finite, and we will claim that. So this is our claim. What is our claim? That A closure equal to A, then A is closed, right? Because the closure of a set is a closed set. If I prove a closure equal to A, then I am done. But we know that, so we know that A closure is always what? A union the derived set of A, right? This is known to us. Now thus it is just thus it is enough to prove that the derived set is empty, right? If the derived set is empty, then A equal to A closure, right? And now what does that mean? If the derived set is empty means that no points of X is a limit point of that set, right? Now so for example, so also I can assume that the set has only single elements, then you are done. Why? Because also it is enough to assume that this cardinality of A is 1. Why? Because if one set point is singleton set is closed, then you know that finite union of closed set is closed. So if you have finitely many points, then take singleton and then take the union, that will be the full set, and that must be closed set, right? Because finite union of closed set is closed in under any topology, right? So it is enough to assume that a closure equal to n. Okay, and so let you choose an element. Say suppose your x1 is the only element inside A, and you choose any set, any point x belongs to X. Okay, such that X your x1 not equal to X. Okay. Now obviously if x1 cannot be limit point of x1 itself, right? Now I will show that if you choose any other point x, that also cannot be limit point if you are inside T2 space. Okay. Now as capital X is a T2 space, there exists say U1 and U2 such that this disjoint U1 intersection equal to phi, and say x1 belongs to U1 and x that belongs to U2. Okay, so this is a disjoint neighborhood. Okay, so what does that mean? That means there exists a neighborhood U2 of X which does not intersect with this neighborhood. So what does that mean? That means this U2 intersection A, which is singleton x1 minus x1, which is phi, right? This is phi, right? So what does that mean? That means your x cannot be, so x cannot be a limit point of that the singleton set x non. Okay, clear? And this is true for any general x. So I choose x arbitrary. So no element inside the space capital X is a limit point of the singleton set X. So what does that mean? So that means that that your A dash is phi. Okay, here your dash equal to phi, and thus A closure equal to A. So A is closed, right? And the moment singleton set is closed, then you are done, because any finite set is nothing but the finite union of singleton sets, and finite union of closed sets are closed. Okay, so this is the proof actually. Now one can ask, what about the converse? Okay, so question, what about the converse? What does I mean? So I mean that if every finite point set is closed inside a topological space, does that mean that is a T2 space? Okay, so you understood what I'm asking? So I'm asking that, so that is, if every finite set of x, a finite subset, I mean finite subset of set in x is closed, then x is T2. So this is my question. This is true. So if you know that every finite set is this, then what happened? Okay, so if you think about this problem, then you know that this problem is not true. Okay, for example, let me write down that answer. So answer to this question is no, this is false actually. If every finite set of this is closed, that does not mean that the space is Hausdorff. Okay, and you need to give an example, obviously. So let me give an example. So okay, so you choose your your x equal to say r with cofinite topology. I hope you remember what is cofinite topology. So cofinite topology I mean the open sets are what? Open sets are those, either it is empty set or the complement is finite. Okay, so that means x itself is complement of x is phi, so it is finite, and all the open sets have finite complement. So what does that mean? That means closed sets are all finite sets. Okay, closed sets are all finite sets. You cannot have okay, I mean so open sets are those sets whose complement complements are finite, and those complements are the only for closed sets, right? Okay, so for example, natural number was closed set inside R with respect to usual topology. But what about inside this topology? Think about it. Set of natural number, if you choose inside R with cofinite topology, is this open set or closed set, anything? Okay, think about it. Okay, so it is neither open set nor closed set. You can check it. Okay, so here you see that this space is actually having the property that every finite set is closed set, because that is the definition of the topology here, right? So here every finite subset of R is closed with respect to this topology, cofinite topology. This is okay, because if it is finite, the complement is those sets whose complement is finite. So complements are open, so this is closed set, right? So the question is that, does R with respect to cofinite topology a T2 space or not, Hausdorff space or not? And the answer is no. That's why I wrote. So this is not a Hausdorff space, not a T2 space. So what does that mean? That means you need to find out two distinct points, and you have to find out you cannot find out the neighborhood of one, like two disjoint neighborhood that does not intersect. For example, okay, so for example, you just start with two elements set. Okay, okay, so let me write down here. So this is my 1 and 2 distinct points. Okay, so I have a neighborhood, say u1 of 1. So what is that? That is r minus 1. So this is my neighborhood. This is the neighborhood of 2, right? This is 2 belongs to this neighborhood, and u2 is r minus 2. This is 1 belongs to this neighborhood, right? Now you see that these two, so whenever you choose a neighborhood of 1, that must contains the other one. Okay, so and sorry, that must there must be intersections. Why there must be intersections? Because the open sets are infinite sets. Okay, and there is the closest are only finite sets, and hence if you take two open sets, there are infinitely many such points, so there must be intersections. Okay, so this is not an counter example to show you. So you need to find out that it is not true. So given any neighborhood of u1 and u2, they must intersect. Okay, that is the proof. So you need to prove that. To prove this thing, that let say 1 belongs to u1 and 2 belongs to u2. Okay, two neighborhoods. Okay, then you need to show that your u1 intersection u2 is not into 5. Okay, that you need to show that. So there must be some points that must belongs to these intersections. Can you prove that? The homework. Okay, so that implies that you cannot find out any two disjoint neighborhood which contains 1 and 2 respectively. Disjoint neighborhood, I mean. So open sets which are disjoint to each other. Okay, and they contains both the points respectively. So this is yeah. So this is kind of the proof of the things that with respect to the cofinite topology, your subset, your space of real number is not T2 space. Okay, but it has the property that all the finite point sets are closed, right? So what does that mean? That means this property of finite points that are closed are not equivalent to T2 space. This is kind of a weaker condition. So what is the conclusion here? Conclusion is that this property of finite sets are closed is weaker than T2's property, T2, right? T2 space, T2 property. Because every T2 space has this property, but I have an example that if you have a property, then it may not be T2. Okay, so then what kind of space is this? This kind of space are actually have a name. It's called Fetcher space or T1 space. Okay, I'm not going to or maybe just let me give one line things and then I am going to. Okay, so this kind of property is called T1 space. Okay, so what does that mean, T1 space? So T1 space means that if you choose any two distinct points, okay, there exists u1 u2 neighborhood of x1 x2 such that so u1 is a neighborhood of x1 such that x2 does not belongs to u1 and x1 does not belongs to u2. Okay, but I am not sure whether they are disjoint or not. So they may not be disjoint. For example, here I have given an example, the two neighborhoods, which like here. Okay, so that see in that first neighborhood, one does not belong to this, second neighborhood, two does not belong to this, but they are not disjoint. Okay, so this is the property. So this property is equivalent to say that finite point sets are closed. Okay, so this kind of space are called Frechet space or the T1 space. Okay, so let me not discuss in details, only I will give you one theorem, and then I am going to my next important theorem. Okay, so what you can have inside this T1 space. So let me just write down theorem. So so let x let x be a T1 space. Remember these all those things, so in details you will learn in later, all the kind of characterization of separation axioms. So I am not going to in details, I am just giving you few ideas which I require for some of the theorems later. Okay, so so A is okay, so A is subset of A is subset of S, and you choose a point, say belongs to A. Okay, is a limit points of these. So or rather you can say it doesn't matter, so I should not say A. Okay, so A is a point of is a limit points of capital A if and only if so this is the if and only. What is the if and condition? If and only if every neighborhood of that point x, whatever the point you are choosing, every neighborhood of x contains infinitely many points of A. This is the important things. Infinitely many, because the finite sets are all singleton closed sets, so the neighborhood must contain infinitely many points. Okay, infinitely many points of A. This is final condition. So inside a T1 space, it is enough to check that a point is limit point or not. If you just choose a open neighborhood of that point and check whether it contains infinitely many points of A or not. I mean this is actually more than what I am saying. We need only one intersection non-empty, but yeah, there are infinitely many points are there actually in T1 space. Okay, and obviously you can understand that T2 space is more stronger than notion of T1 space. So every T2 space is T1 space, that I just proved it. Okay. Now let me give a proof of this theorem. So the proof is also very simple. This is if and only condition. One part is obvious. So if every neighborhood contains infinitely many points, so if every neighborhood of x intersects A at infinitely many points, then obviously then so with, obviously if you remove that, right, because the intersection of infinite, if you remove one point, it doesn't matter. So thus x belongs to the derived set of, right, A. That means x is the limit points. Now conversely, let u be a, let if we suppose assuming, so you are assuming that x is the limit point of A. So so let x belongs to A dash and u be a neighborhood of x such that it intersects finitely many points such that u intersects a minus x is finite, something finite set x1 x2 something like xn, finitely many points are there. Okay, then I will find out the counter example. Then I will show that this is not possible. If the intersection is finite, then what happens? You remove this. See, this is a closed set. Finite points is a closed set in T2 space, right? So if you remove this x minus x x1 x2, okay, I don't need x, I just need this is enough for me. x1 x2 and so on xn. Okay, so this is a open set, right? Open neighborhood of x, right? Because x belongs to this set a minus this, and also this is open because this set is closed inside T1 space, because this space is T1 space, right? So this is open neighborhood of x, and these neighborhood intersect with a minus and so this, let me write down a name here. So this maybe u dash, this is neighborhood, and see that u dash intersection a minus singleton x is actually empty, which is a contradiction to the fact that x belongs to derived set of a, so it's limit point, right? So you find out the neighborhood such that it does not intersect with a minus x, so it cannot be. So what does that mean? That means this intersection is always infinitely many points should be there. Okay, and then the last but not the least, what I am going to prove, and we will finish my lecture, that in a T2 space, if we have a sequence, that we will converge always at most a 1 point. So the limit is always unique. Okay, if the limit exists. Okay, so so theorem. So in a T2 space, limit of a sequence is unique if it exists. I am not saying it always exists. Unique if it exists. So what does that mean? That means it cannot have two limits. Okay, so the proof also is not so difficult, because the T2 property will force to the limit are unique. Okay, so how to prove it? So suppose you have a sequence, so let you have a sequence xn which converts to x. Okay, I know, suppose I am assuming that the space is T2 and it has a unique limit, and you assume that there is another point, and I will show that, and let you have some point say y which is not equal to x, then we will show that y cannot be a limit of the sequence. Okay, and why can we limit the sequence? Because x is a T2 space, so there exists, say, u1 and u2 neighborhood of x and y respectively, such that what happened? X is inside u1, y is inside u2, and u1 intersection u2 equal to phi, right? This is the neighborhood. Okay, so as xn converts to x, obviously there exists some natural number belongs to natural number such that xn belongs to u1 for all n greater than equal to n naught by definition, right? So what does that mean? maximum finally many terms can be outside U1. Everything is inside U1, right? So what does that mean? That means thus V cannot contains infinitely many points of the sequence xn, right? Sorry, what is my U2, not V? Yeah, so U2 cannot contains infinitely many points, right? But because this is a T2 space, this is also T1 space, right? Because every T2 space is T1 space. And for T1 space, we just proved that a point is limit points if every neighborhood contains infinitely many points. But here you find out that you have a neighborhood V2 that does not contain infinitely many points of xn, and thus y is not a limit point of the set. If you can think this is a set, so or rather limit point of the set sequence of number means limit of the sequence. Okay, as T2 space are also T1 space. T2 space are also T1 space, right? And inside T1 space we know that whenever the points limit points, then every neighborhood of that point contains infinitely many points of the infinite point of the set X. So this is the proof that shows that inside the Hausdorff space, if a sequence has a limit, that must be unique. It cannot have a 2 or 3 or 5 many limit points. Okay, so I will stop here now, and yeah, so this is today's talk. I will stop here now.